Welcome to Ask and Learn.
All right, so today we're going to talk about problem 1 in chapter 4 of Principles of Biochemistry textbook. This is going to talk about the strengths of peptide bonds and kind of some of their characteristics. So some research was done a while ago, and they found out that a peptide bond, which connects two amino acids, so that would be this bond right here. So this would be our first amino acid. This would be our second one. I didn't really draw that in. And the bond that connects the two of them, the peptide bond, is actually only 1.32 angstroms. And this is weird because it's shown as a single bond, a carbon-nitrogen single bond, but a carbon-nitrogen single bond is usually 1.49 angstroms. So our peptide bond is a little bit smaller than that. And then what gets even weirder is a carbon-nitrogen double bond is 1.27. So it's still a little larger than a double bond, so it can't be a double bond. And so we can figure out why this happens by drawing out resonance structures. So if we scroll down here, I have another amino acid pair drawn, partially drawn. And again, our peptide bond is that bond between the carbon and the nitrogen of the two amino acids. And what can happen with resonance is we have a lone pair here. So this lone pair can participate in resonance. We have a lone pair next to a double bond, and that is one of the trends for resonance. So we can go ahead and bring these electrons within that lone pair to share between that carbon and nitrogen, create a double bond, and we can move these pi electrons and create a lone pair. And what happens with this What happens with this is we create a double bond between that carbon and nitrogen, and then we create two charges. So, and when you have a resonance structure, it does not exist in these two separate forms. Basically, these electrons can move all throughout this little area right here. And so what we can draw is a depiction of what it might actually look like, is with these single bonds and then partial double bonds. And that's how it's kind of going to exist. We have a partial positive charge there, partial negative charge there. And so this makes sense because we have something that's stronger than a single bond, but weaker than a double bond. So for strength, it's stronger than a single bond and weaker than a double bond. And this helps us clarify this length issue because we have something that's shorter than a single bond. Double bonds are shorter than single bonds, but it's not quite as short as a double bond. So we have this like half pi bond that's forming. Okay, so our strength question is answered. For bond order, our bond order is probably going to be something like 1.5 because it's in between a single bond and a double bond. So a bond order for a single bond would be 1, bond order for a double bond would be 2. This one would probably be more like 1.5, and we can kind of justify that in that the lone pair electrons are going to spend some of their time within that double bond, but not all of their time during that double bond. And this would make sense too, because what they also found is that this is planar. So this part of the amino acids connecting sits flat, and normally this would not sit flat. This nitrogen would not sit flat with a lone pair in there. And so since it forms that partial double bond, it's actually going to lay flat to make it easier to form that double bond. We have to remember resonance stabilizes, and so anytime there's resonance, it wants to participate in that resonance to make the molecule more stable. And then our last part of the question is, what does it mean for rotation? So normally, if you have a single bond, if we just draw a structure here, skeletal structure, this bond can rotate, and it can exist as this form, but it can also exist as this original form because that carbon can swing around and rotate. And this can only occur with single bonds. Since we have something that participates in resonance and is not just a single bond, it's a little bit stronger than a single bond, and it does have these pi electrons, it can't rotate. So it's going to act like a double bond. So double bond, you can have a cis double bond where the legs are on the same side, or the substituents are on the same side. But you can't just flip from a cis to a trans. You can't do that because this double bond is there and it's preventing that rotation. So this cannot turn, this peptide bond. So it's planar. And what will always happen is that these alpha carbons will end up trans to each other. So you're not going to see an amino acid bond to another amino acid and create something where the alpha carbon is right there. That's not going to happen. It's more stable for that alpha carbon to be trans to the other alpha carbon. And it can't rotate because of that partial double bond, or that bond order of about 1.5. My recommendation is that anytime you're stuck on problems like this is to just draw out, think about, is there resonance? Think about the reasoning behind. I hope that helped. Thanks.